Hello everyone, and thank you for giving me the opportunity to present my work at this workshop. My name is Timotheos Souroulla, and today I will be your presenter. And at this slide, you can also see the names of the other authors of this work, and the title of this work is called Model Compression for Resource-Constrained Mobile Robots. And let's begin with our introduction and the basic outline. So our work focuses on applications where IoT devices are employed in scenarios where high complex deep neural networks are used. And in such applications, there are some constraints due to the limitations of the computing and energy resources of these IoT devices. So here comes in play the model compression. And model compression in one sentence aims to reduce the complexity and the number of parameters of such deep neural networks and the neural network models by removing redundant operation. And the use case that we use in our study, we can see the screenshot on the right, and our use case was a human-robot collaboration scenario. And human-robot collaboration scenarios are scenarios where both humans and robots work in the same environment at the same time. And due to this collaboration that they share the same workspace, a proper safety analysis is necessary and is performed from the robots to avoid any hazardous situations, for example, colliding with the human or with static obstacles. And this safety analysis is a highly complex procedure that uses deep neural networks. And these mobile devices, which are mobile robots in our case, rely on edge infrastructures to execute these complex tasks. But in some cases, the edge may be unavailable or a connection to it may not be possible. So here comes the motivation of our work and the question, what will happen when the edge is unavailable or a connection to it is not possible? The mobile device still needs to navigate safely around the warehouse and react in real time with static and dynamic obstacles. And this work aims to overcome such issues of the unavailability of the edge by using model compression techniques to reduce the complexity of computer vision algorithms and aims to execute everything locally at the mobile device. And here comes our research question. How can we reduce the computational requirements of computer vision algorithms using model compression techniques while keeping their accuracy at high levels? So basically, how can we reduce the complexity of a deep neural network while keeping the accuracy at high levels? And by having said our motivation and the short introduction, I'll now explain the model compression techniques that we use. And we can make a division of the model compression techniques into two main categories. The first one that reduces the number of parameters and the total inference time of a model. And two such model compression techniques are pruning and knowledge distillation. And the second main category of model compression techniques aims to reduce the total inference time of the model without reducing the total number of parameters. And two techniques of this category are DNN splitting and neural filtering. And in our case, we use pruning and knowledge distillation because they are the most popular ones, and literature provides evidence that they have good results. And I will now explain shortly pruning and knowledge distillation, beginning with pruning. And in pruning, we learn only the important connections of a deep neural network, and we discard the non-important connection. So, for example, we remove redundant operations such as addition with 0 or multiplication with 1, and we remove them from the model and we eliminate them efficiently. And there are several different pruning techniques that one could use to achieve this. And I will explain 4 of them in total, beginning with random pruning. In random pruning, the user selects a percentage X, and X percentage connection from the whole network are removed regardless their weight or their layer they belong to. And we can see from the example on the right that for every different run we do for random pruning, we may end up to a different neural network. And that's why it's called random. And now moving to the class distribution. In class distribution, the user selects a global threshold T, and for each layer, the standard deviation sigma is calculated. So for each layer, we have the standard deviation multiplied by that global threshold, and we have the layer-wise threshold. So we have sigma multiplied by t, sigma 1 t, and sigma 2 t for each given layer. And that's our threshold for each layer. So every connection that has lower weight than that threshold is removed from the model. And here the challenge is to find the optimal threshold t. And that's why this is a bit challenging one to use. And moving on to the class uniform technique. In class uniform, this is done layer-wise, and the user selects again a percentage x, and x percentage connections are removed from each layer, and this is done layer-wise. So from each layer, the 50%, for example, connections with the lower weights are removed. And the last one is called class blind, and is quite similar to the class uniform. So the user again select a percentage x. But in this case, the pruning is done globally. So the X% connections with the smallest weights are pruned regardless of the layer they belong to. And we can see from this example that each technique ends in a different neural network. And we can see, for example, the connection with marked with 2 here is removed from both models, but the connection with the 5 here is removed, but here is kept in the model. And moving on to the knowledge distillation. So in knowledge distillation, we have two models, the teacher and the student. The teacher is the large and the complex model, and we replace it with the student model, which is trained to mimic the output of the teacher model. So we have the large teacher model replaced by the student model, and we'll see an example later on. And the key assumption here is that the teacher model, large teacher models are often over-parameterized and can be compressed without any significant performance loss. And here is the example that we have a large teacher model that is complex and has more hidden layers. And we replace it with the student model that has the same number of inputs and same number of outputs, but it's less complex and much smaller one. And moving on to the experimental implementation. So in our experiments, we used this metric. So we had a trade-off between the accuracy drop and the compression percentage. So as in the research question, we wanted to compress the model as much as possible, but we aim to keep the accuracy at high levels. And we divided our experiments into sections. So we had object detection and semantic segmentation. And we used different data sets for each one. So for object detection, we use Cypher10, and for semantic segmentation, we used Pascal VOC and Pobble datasets. And here we can see the models we use. We use these models that were easily imported from the PyTorch library, and also their initial number of parameters. So for semantic segmentation, we used FCN ResNet 101 with 54.3 million parameters, and MobileNet V3 with 11.1 million. And for object detection, we use LINET, ResNet 18, and ResNet 101 with this number the initial number of parameters. And we performed 3 different experiments. So we began with pruning, just applying pruning on the models, and used 3 different pruning techniques: random, class uniform, and class blind. And our goal was to decide which technique performs best and use it for the next experiment. And we didn't use class distribution with the global threshold T. As I mentioned earlier, it's challenging to find the optimal T. And then we applied only knowledge distillation on different combinations between the models as teacher and student. And our goal was to decide which combination performed well enough and use them for the next experiments. And we can see that we used 5 different combinations, and each arrow here represents a combination. So beginning from the teacher model ResNet 101, pointing to the student ResNet 18. And then our third and last experiment was the novel part of this study. So we applied first knowledge distillation on the best combination found from the knowledge distillation experiment. And then we used pruning on the resulting student model, using the best pruning technique found from the pruning experiment. And our goal here was to see whether the combination of these 2 techniques perform better than the standalone versions. And we can see the pipeline here that we begin with a large teacher model, compress it using knowledge distillation, getting a smaller student model, and then use pruning on the student model and getting an even smaller one. And now moving on to the results, beginning with the pruning experiments and the object detection. So we had 3 different models, LINET, ResNet 18, and ResNet 101. And we can see from these 3 figures that in all cases, the yellow line, which is the class blind technique, performed better in all cases. And by having a closer look at the results, we saw that almost in every case, for every pruning fraction and for every pruning percentage, the class blind outperformed the other 2 techniques. So it was safe to say that class blind technique was the best performing pruning technique and use it for the upcoming experiments. And for the semantic segmentation, we had an interesting result that no matter what the pruning fraction we applied at mobile net v3 for 2 datasets, COBO and VOC, we had pretty much a steady result without any significant accuracy drop. So we decided to add it as a future work and do some further investigations. And now moving on to the knowledge distillation experiment. So we used 3 different different combinations for the object detection. ResNet 18 to LINET, ResNet 101 to ResNet 18, and ResNet 101 to LINET. And we can see the accuracy of the teacher model and the accuracy of the student model, as well as the compression percentage. And we saw an interesting behavior here that was also mentioned in the literature, that in some cases, the accuracy of the student model, like the second and the third case, was higher than the accuracy of the teacher model. So this is basically happening because of the better structure of the student model and getting better results on our dataset Cypher 10. And at this point, we selected the second and the third combination, the first and the second combination. So the third because it achieved accuracy higher than 85%, and the second one because the compression percentage was significant enough to see the results by applying pruning afterwards and not having 90% compression percentage and then applying for 99.5. So we decided to move on with these 2. And for the semantic segmentation, these were the results. So for both data sets and this combination, the accuracy of the student model was higher than the teacher model. And we have a compression percentage of approximately 80%. And moving to our last experiment. So we used ResNet 18 as teacher and LINET as student model. And we had the knowledge distillation and then pruning. And we can see the results here that we began with 93% accuracy and 11.2 million parameters. And we ended up with 300,000. So we removed 11 million parameters from the model, and we had an accuracy drop of 10%. So our compression percentage was 97%, while the accuracy drop was 10%. And we still achieved accuracy higher than 80%. And moving on to the next one, the next combination, ResNet 101 to ResNet 18. And we can see that beginning with 44.5 million, we ended up with 5 million. So we removed 40 million parameters from the model. And we achieved accuracy higher than the original one by 2.5%. So we had a 90% compression percentage and we had an accuracy increase, not an accuracy drop here. And for the semantic segmentation, we noticed that we began with 54.3 million parameters, and if we prune the model more than 20%, the accuracy drop was increasing exponentially. So our results were, we had 85% accuracy with 10 million parameters, so we removed 44 million parameters and we had an accuracy increase. And after that, it was a sudden drop. So we decided, our result was that the combination of the 2 techniques performed better than the standard version. And for object detection, the best performing combination was the second one, as it had lower accuracy than the first one and the same reduction percentage in number of parameters. And in semantic segmentation, as I said, there was a significant accuracy drop for pruning fractions higher than 0.2. And some conclusions: we managed to compress ResNet 18 by 95% without any significant loss, 10%. ResNet 18 by 90% and have a higher accuracy. And ResNet 101, FC and ResNet 101, we compressed it by 82% and we had accuracy higher than the original one. And at this point, it's worth mentioning that the accuracy drop depends on the application. So for medical applications, even a 0.1 accuracy drop is may be crucial. But for other cases, a 10% accuracy drop maybe zero might be acceptable. So depending on our use case, we have similar, we can compress the model as much as we want. So we have noticed some positive effects in applications where high complexity neural networks are used, and as we succeeded to reduce the number of parameters, and we managed to keep their accuracy at high levels. And the assumption that large models are often parameterized is confirmed. And ending up this presentation by some future work is to employ DNA splitting and neural filtering and perform more experiments. Test the best performing model on an actual robot and integrate this work in the safety framework of the general project. The next one is the most important one, that is to compare a compressed model with an already smaller model like your ones, and see if it's actually worth it to compress a model rather than using a smaller one from the beginning. And we also introduce model compression in more use cases and not only in an HRC scenario. And last but not least, to do some further investigation on semantic segmentation. And at this point, this is the end of my presentation. Thank you very much for your attention. You can also see some references here. Thank you very much for your attention, and thank you for giving me the opportunity to present my work here. Thank you.
So let's thank the speaker. Let me stop sharing my screen.
Thank you for giving me the opportunity to present.
Oh no, wait, that's still a recording.
My name is Timotheos Souroulla, and
yeah, okay, there you go. Let me just check. Timotheos, are you there?
Yes, I'm here.
Hi. Okay. Right. So do we have any questions? I have one quick question. So very interesting presentation. So thank you for that. I could see from your results that you were comparing a lot of accuracy versus compression of the models. Did you consider also maybe including computation results? Because it's not clear to me how much the compression that you could, make with your approach was actually beneficial. So how much would it actually cut time off of the machine learning process? Now, I know that this is going to be specific to the hardware that you're using, but I was just wondering if you consider that including those results in the future, because I do think it would be useful to know.
Yeah, so your question is how about the inference time of the results, right?
Yes.
Yeah, we are considering that factor as well. Yeah, but we noticed that it had the same, how do you call it? Yeah, the same behavior as the number of parameters, more or less. So that's why we didn't include it in our paper.
Okay.
But yeah, there are more figures about the numbers of parameters and how they behave when there is compression on the paper. Yeah, I couldn't manage to fit everything in the presentation. But yeah, there are more details in the paper and also in the publication. Yeah, the DIVA portal of KTH.
Perfect, thanks. Yeah, I think it will be very interesting when you put it on the actual robot as well to see how much impact it has, because robots are very well known for having a lot of constraints on resources. So yeah, I'm looking forward to the next version of the paper as well. So thank you very much. Any other questions? Okay, so because we are a little bit short on time, I think we'll move on to the next paper in the session, which is also online. So